Except Ruben, if you're watching, this doesn't apply to you even. Hello gamers, my name's jumpVids and welcome back to the second edition of the Fundamentals of Imperative Programming with me, jumpVids. I streamed this yesterday, But then OBS was like, oh, by the way, your connection's dead. And I was like, okay, cool. But then like it said reconnecting, the stream's still going, we're all good. And then YouTube was like, no, we didn't get like the last 80+% of your stream. I'm like, no, so it's gone. But it's okay, because I get to give it another stab, so that's what I'm going to do today. Redoing the stream. How are you, Kayoshi, in the chat? Second edition, yeah, I really should put second edition, but like second edition is for if I do a video and then I'm like, I want to redo it because I want to make it better. But here I'm redoing it because I have to, because the old version's gone. Yo, 2 viewers, welcome to the stream, guys. Is that Ruben or is that someone else? If it's Ruben, then hey, Ruben. The only reason why I want to know if it's Ruben or not is because I made 2 videos prior to this and I don't think Ruben's seen them, so if that's the case, I'm happy to re-explain. Just so Ruben's on the same page, but if not, then that's fine. I'll sort of assume that you've seen the videos I put up on the thumbnail at the beginning. If you didn't catch that, that is these 2 videos over on my Cool Computer Scientist channel. They're like 2 of the most recent ones. One on graphs and one on functional entities. Alright, so assuming you've got that, let's begin the stream. Alright, so I did this previously. I did it pretty well. I don't know how I'm going to do it as well as I did the first time, which is gone now. But what I thought would be good is that at the end of this stream, I did like a summary. So I did a bunch of stuff, and then at the end I was like, oh yeah, I should summarize what I've done so far. But I thought it'd be good to just copy paste this and use this as my intro. So this is essentially, oh wait, I need the other bit too. I'm done. What done? One sec. Here it is. I just realized I need the diagram too. So this is essentially what we're going to be. Whoa, why did it do that? That's weird. Why is my software doing that? I don't even know. Oh, please don't do that. Computer. Oh, it's going to be like that. Oh well. I can just retype it actually. It's all good. Oh, it's because I've got a white selected color. What? So many problems. There it is. Alright, one sec, let me just rewrite it. Hopefully it won't take me too long. There we go. And then the diagram here is gone, but we'll look at that very shortly. What's the, oh, I should do like the equals to itself symbol. I don't know how you actually draw a symbol, but I know there's a symbol in maths where like equals, and you just point it back at itself. We'll do that. So these are the things we're going to be looking at. We're going to look at the difference between memory and storage. We're going to look at a model of the CPU that's better than like the standard one of a CPU equals the brain of a computer. We're going to be looking at CPU as a calculator instead, because I think it's a better model. And we're also going to be looking at how the CPU executes step by step through programs, which seems obvious if you've done a lot of computer science, but this is sort of looking from like the fundamentals of if you've done no computer science before, looking at all the things that aren't necessarily if you've never done any computer science before. So I'm sort of assuming the prior knowledge that I put at the start of the thing. I'm guessing you've seen that. So let's begin. So first of all, we need to look at this diagram here, which died because my software's done. I'll just redraw it, it's fine. So this diagram is essentially going to give us the, oh, I should look at the list. I'll look at that. One sec. This list here. So we've done these 2 in previous videos, and we're going to do these in later videos probably. And so before we can go to the later videos from these videos, we need to do this one in the middle, which sort of bridges the gap between, I sort of spoke about this the first stream but got deleted, of how in the first half we essentially have maths, and then in the second half we have computer science, and this one's like bridging the gap between just straight up computer science of computer programming. How do we make the computer do the things that we want it to do? And obviously you can use applications by other people, but essentially we're looking at if there were no applications, or if we want to make new applications, how do we make the computer do what we want it to, which requires computer programming. But this is sort of in the middle, and you know, let me just draw this diagram. Is this making any sense? Yeah, when the diagram's equal to the diagram, you know, you just got to use all the mathematical constructs you can when they're useful. All right, so this model we're going to look at for what a computer is, which is a pretty useful model, is we're going to declare it's going to be a graph of 5 nodes. And the 5 nodes are HDD, RAM, Oh, how are you, Keishi? I don't know if I asked. I was talking to you on Discord just before the stream, so I'm guessing you're okay. You're working on the Lewis script, right? You know, done with that. CPU. Input node goes here, and then we've also got an output node that goes here. And because we've only looked at one type of graph, which I looked at in the first video, called directed unweighted graphs, that's what this is going to be, because that's the thing that we worked with. So we're going to have a bidirectional edge here, meaning this relates to this in the same way this relates to this. It's like a mutual crossover relation. You can sort of, like I said before, you can imagine it as two arrows, except we don't draw either arrow because it's just neater and stuff. And if it's just an edge, just a relation like that, we assume it's bidirectional. But then these ones are actually going to be directed, so we're going to go into the CPU, and then from the CPU out to the output node of this graph. Water go brrr. Oh yeah, gotta stay hydrated, man. It's because basically the lighting in my room's not great, so I was like, how can I make the lighting better? So I have like this massive lamp over there that's really hot, so gotta drink water to counteract the heat of the lamp. Okay, what we got going on here? It's a very good question. And essentially what we're doing is, if you have a computer and you look at it, the first thing you sort of see is like a monitor, keyboard, mouse, whatever. But there's actually a lot of components within the computer, and that's what I was sort of talking about the first stream. In fact, I talked about it really well there, so I'm going to yeet and copy my explanation from there. But essentially what I was talking about is how within a computer, in reality, it's not just like 2 or 3 things attached. There's like all sorts of different wires, electrons, electrical currents, all sorts of various transistors and stuff going on. So if we were to have a model that really accurately described a computer, it would look like a jumbled mess like this, is what I was saying. And the thing is this is just chaotic to try and use. Like the example I gave is if I'm just trying to write a computer program like here, where we just got, hello Python, you gonna work? Please work. Excellent. So it's like here, simple program, I just want to put 10 in variable x, raise it to the power of 15 and print out the answer. And in this case, that will give us 1 followed by 15 zeros, because that's 10 to the power of 15. If I just want to do a simple program like this, there is absolutely no reason why I need to understand every single component within a computer. That's too much information for just writing simple 3-line computer programs. So this is one way, and I describe that as the electrical engineer's perspective of a computer. And for an electrical engineer, you need this. But if you're just going to be writing Python scripts, which is what we're looking at in this series, really just getting up to writing programs in a standard language, you don't need to understand every single component. So this model, like for us, it's just too much. So we can ignore this. It'd be better to ignore this. There's just too much going on. But in the same way, like the other way isn't good either. Like, for example, there's very simplistic ways we can think about a computer. I mean, if we wanted, we could think about a computer as a single node in a graph, but like that's no use to anyone. And another model that we looked at in the past video called a functional entity, as useful it is to begin with, this sort of graph of just 3 nodes describing a computer is too simple. It doesn't give you enough information about the computer. So what we have here is we have a nice middle ground between considering every single physical piece of a computer and just looking at the important mathematical details. This is a really good way to think about it. So I guess what we should do is talk about each of these nodes so we can understand this model fully, because this model is going to be really important if you want to get into computer science and programming. So what do each of these things mean? Well, we could look at the logical meaning of each one, but what's actually quite nice is that these 3 all have in common is that they're actual physical devices, which makes it a lot easier to think about. Instead of just thinking about a logical, mathematical thing, if you can actually hold it and feel it, which is what you can with these. So I went onto Google and got some images last time midstream, but I don't have to this one because I can just copy paste the things I already made. So let's do that. Did I put my microphone on? I'm so worried I didn't. I know I did, but I'm so worried. No, I'm talking. Okay. That moment you're like, oh no, did I mute myself? But no, we're good. So these are the 3 components that we're looking at here. So the HDD is this guy here. Looks like this. It's a pretty big computer thing. You may have seen one before. You can get external hard drives too. I think I have an external hard drive. I do. This is like the HDD is like a physical thing that you can hold. But we've got a picture of another version of a HDD here. They look kind of like that, pretty big and bulky. Then for RAM we have this guy over here. Boop. A lot skinnier. And this is actually quite useful because logically it is smaller as well as being physically smaller, which is quite nice. Helps to remember the difference between HDD and RAM, which is an important difference to be able to tell, and also similarities, which we can look at. Where's the final thing I'm looking for? Is it here? Here it is, everyone's favorite, CPU. And that'll go here. So even though really as a programmer you won't really think about them as physical things because you don't need to, and because you'll get very comfortable with the idea, it's nice that they are physical things. These aren't, well, these kind of are, but these ones are better to be thought about as logical. So this is the HDD, that is RAM, and that is the processor. But what's more important than the physical things, which is quite important as well, I guess, if you're putting together a computer, is what they do logically. So essentially, the way to think about it is these both come under the umbrella term of memory, but despite both being like memory, essentially, and what we mean by memory is that it stores things. So you might be storing files, images, pieces of code, music, etc. We actually have a specific word for each one. So we call this one a storage device, and this one a memory device, even though they're both sort of memory because they both remember things, I guess. And the difference is that a storage stores every single thing on your computer. So anything that's stored on your computer will be in the HDD, in the storage unit, whereas the RAM only stores the thing that are currently active. So it's quite an interesting thing with computers. You always tend to have more files, more codes, more applications than you'll ever have running at one time. So like, for example, on my computer, as you can see on this bar here, just off to the side over here, I have like a long list of every single application on my computer, and there's like 20 or so different icons here. But you can see a dot next to it. Maybe it might be too small, but essentially I have like a dot. So like, let's imagine these are my applications. There isn't a dot next to all of them. There's like, you have this many applications, but there'll only be like a dot next to, say, this one and this one. So it means I've got all these different applications that could be running, but only of those are a very small proportion of them are. And that's what happens with HD and RAM. You store a lot of things, but you only have a certain number of things open, and when you have it open, it gets copied. A copy of that data gets put into RAM. And that's important because the processor, which you may have heard as like the brain of a computer, but I don't think that's a good model. I even got a picture of a brain. I don't know why. Let's have a look at the brain for a second. I don't know why I got this, but I did. But I don't think that's actually a good model. You know what? I want the picture of the brain on here. Let's bring it on. I'll take like 2 seconds to put on, right? Completely unnecessary, but at the same time very necessary. There we go. Oh, it's huge. Fantastic. Let's just put it over there. Oh, let's give it a smiley face as well. Excellent. Yeah, so it's quite nice to think about the CPU as a brain, but it's not very realistic. And not only is it not very realistic, but I actually would go as far as saying is it's not helpful to think about as a brain, because brains have weird intellectual biological things they can do, but a processor doesn't do anything intellectual. It just does, well, I'll sort of explain. A better way to think about the CPU is as a calculator. So I actually got a physical calculator as a demonstration last time. I don't know what I've done with it. Oh, there it is. Wait, physical calculator. And I don't know why people don't use this analogy more. I'm going to draw a calculator here because I can. But essentially, a calculator is a much better way to think about what the processor does. And the only differences between a calculator and a processor is just how quickly it does it and how it does it. So like a calculator, even if you're really fast on the buttons, you're only going to do like 3 or 4 calculations per second, say. But a processor does like 2 to 4 billion calculations a second, which is like staggering to think about. So I'm going to put this here. Just let it sit. Like that's a ridiculous number of calculations. And so because like as a human you couldn't keep pushing buttons that quickly, it isn't like a calculation that you push it in. What you do is you'll set up like 1 billion calculations and then you'll pass it into the processor and say, here, do these one by one. And essentially that is the fundamentals of imperative programming, which this series is all about. Is the I talked about this before, but not all programming is imperative. So you also get declarative, but everyone always talks about imperative and everyone knows and loves imperative. People don't talk about this so much because it's much harder to think about. But within this paradigm, which is the most common one, like all computation, how we use computers, how computers work, and how you make the computer do what you want it to do, is based on this fundamental model of you want your processor to do loads of calculations, you create a list, and it goes through them one by one. And that is essentially what this video is about computers executing a long list of instructions one by one. So Covered quite a bit. Is there anything else to do? Oh yeah, input and output. So we spoke about this. This isn't too bad, I don't think. You store everything on the computer. Of everything you store, you run the things that you want running in here, which is going to be a small proportion of the things that are all stored. And then these things are a long list. RAM or memory is just a long list, is the way to think about it. And then the processor will go through this list one by one and execute them. But these things I haven't really spoke about. These are more just worth being aware of. You know how I talked about the functional entities last episode, how the computer is a functional entity? Well, essentially, it is, except these two things add on, but then here is just the same model we looked at before. So you put things in, the processor does its calculations to think about what you've done. Well, not think, but process, and do the calculations required to process your inputs, and then we'll give an appropriate corresponding output. So like if you want to know, say you tell the computer I want to do 5 plus 4, it's not just going to print out 72. If you ask it what is 5 plus 4, it will give you what you want to know, which is 9, is what an appropriate corresponding output is. But that's not too bad. People are sort of more familiar with this idea. And people are pretty familiar with this too, but I guess just in case, it's worth covering. If that's making sense. Yeah, huge brain. Sorry, I'm responding to your comment like a million times too late. Alright, I guess one more diagram. Did I cover everything on the video? On my checklist of things to do. So we covered the diagram, covered memory and storage, we covered processor calculator. I guess just one more thing, and then I'm done with this stream. Let's go. But if anything didn't make sense or you want me to clarify anything, please do say in chat. I just have no. I've never communicated this in front of a live audience, so I don't know how clear or otherwise these explanations are. So if there's anything that isn't, then feel free to be like, Josh, nothing makes sense. Explain this, which would be cool. Alright, where is it? I drew a much better diagram last time. I don't think I could top what my diagram was last time, so I'm just going to reuse it. Here it is. So this is for visualizing what's going on. So essentially, when you... Oh, let's write a program. What better way to demonstrate than to just like do it? So let's say we had a diagram. Oh, this is why I wanted user interaction this time. Anyone got any ideas for programs? What are we going to compute? Nothing too taxing, but it can be a bit crazy. We could do all sorts of creative stuff. If I've got viewers who are interested. If not, I'll just come with some bog standard stuff. I'll start an idea I have. Oh, I just realized stream delay means I'm going to say, hey, got any ideas? And then there'll be nothing. All right. Yeah, I don't know either. I don't know if there's anyone else in chat. That's okay. So let's say that we need a... I was going to do... What the people do these things. They do like love calculators. Computing powers of 2 modulo 97. Oh man, you're testing my computer science here. 2 modulo 97. What do you mean by powers of 2 modulo? Oh, okay, yeah, no, that's good, that's good. I can appreciate that. Let's do that. Oh, this is great. The nerdiest example program I've ever done. Wait, I shouldn't use functions because it's just a step by step. So we'll do amount equals powers of 2 modulo. So we're going to do power of 2, input what power of 2 modulo 97 do you want? Oh man, it doesn't get much nerdier of an example than that. I love it. Oh, we need this to be an integer. 1 second, I'm being a casual programmer. Oh man, there's a lot of logic already going on in my program. Wow. A lot of logic in terms of if you're new to programming. That's quite a hefty first line of code to be introduced to. And then we just need 1 line to sort all the rest. We probably should use another line just to keep the logical complexity down. Oh gosh, I don't know how to keep the logical complexity down. It's too much computational complexity. So we're going to raise 2. This is raised to the power of. So raising 2 to the power of amounts, which is a user inputted value. And then on here we're going to do modulo 97. And then we're just going to print out calculation. Oh, I trust Kyoshi to make your stream spicy. It should always be this. Oh, I got so trolled. But let's see. That's interesting. So that should always give me the same answer. Really? No, because I can do different powers of 2. Or have I done something wrong, Kyoshi? Or have you, who's made a mistake? Have I made a mistake? I reckon there's going to be different answers to this. Either you've made a mistake or I've made a mistake. We'll find out. It's going to be great either way. What should I call it? Hello World Advanced is what we've just created here. Hello World Advanced.py. Because usually do a hello, like, okay guys, just to pin out. Usually your first program will be like hello world, but instead we've got this crazy mathematical computer science going on because she wanted to add some spice to my stream. All right, and will it work? I reckon we're going to get different powers. You made the mistake because you were saying it's going to give the same answer, but I reckon it won't. Like if I do 3, that'll give me answer 8, but if I do 5, 6, it'll give me answer 64, and 64 is not equal to 8. Like an ask the computer, is 64 equal to 8? No, unless I've made a mistake, or I didn't understand what you meant, something like that. But anyway, so yeah, what does the program do? The answer is a lot of complicated math stuff, basically. We'll go into it a bit. So what we're doing, no, I don't want to go into modular arithmetic, that's a whole nother video. But you can appreciate it's doing a calculation. You put a number in and it gives you an answer out, and if you're a mathematician, you can appreciate how this relates to this. And if not, you really, it's just randomly give number, output number. We're not going to be looking into why this works today because it's beyond the scope of this video. But you can see the idea. We list some calculations in order, and then we click go, and then the computer calculates in order. And sort of to link back to the model I was talking about in this video, we wrote the code, and then before we could run the code, we had to store it. Where's my diagram? Oh, how many different files? Deary me. Here it is. So yeah, so we made a program, we stored it here. Now what we do is we push the F5 button, which is run in Python, and when we push F5, it stores a copy of that program from the hard drive, from my desktop, where the file is. We can actually look at the file on the desktop. Oh no, we can't because it's not on the desktop. If we put it on the desktop. So here's our world, hello world advanced.py. So we put it on the hard drive, then when we click the run button, it copies all the code across into here, and then we give the processor steps one by one. So it's in here. What does it look like in here? That's a great question. We can move over to our second diagram, which is, oh gosh, so many slides. No, where is it? Here it is. So we click the run button, and what it does is it splits up this code into machine versions. So these are written in a human high-level language, we call it, Python, and we can read this, but a computer can't, so it switches it up into what's called machine code and stores each of those. In reality, it's not a one-to-one pairing, so for every... Where is it? Here it is. So here we've got, it's not going to be 3 instructions, this will split into probably like 10, 12 instructions, but for now you can sort of imagine it going one-to-one. So you've got instruction, instruction, instruction. If we imagine the code was a bit longer, we can make it longer by just copy-pasting. Imagine it's 6 lines long. You'd split it up into 6 instructions like we got here. And then we've got the inner workings of a processor are crazy. That's what this diagram was meant to represent, just how crazy it is. But you essentially have this logical thing called a program counter. We're not going to be talking about program counter too much. But essentially what it does is it steps through the program. So it starts at 1, and then this gets passed into the processor, gets executed. And then after it's done that, the program counter moves down onto the next instruction. And it keeps doing that. So you execute the instruction, you move down. And because it's stepping through RAM, it can't step through the hard drive, the HDD. That's why we have both the HDD and the hard drive. Where's my diagram? Here it is. So that's why this is needed to store all the various things humans like storing on computers, but we don't execute all the things we have stored, and when we execute it, we can't execute it from here because it needs to be in here so program counter can step through it. So move it into RAM, into memory, so it can do that. And then it goes through the instructions one by one, executes it through, and you have your processed output, which in our case will give us, if we say, what's 2 to the power of 3 modulo 97? Then it's 8. What's the big power of 2? Kyoshi, how big do I need to go? 10. There we go. So 2 to the power of 10, that's 1024, I believe. Let me check. Yeah. And then 1024 modulo 97 gives you your 54, which is what this program does. So there you have it. You put in your values, wait, we can relate this all to the diagram. The diagram is very important because it allows you to explain things really well. Here it is. So put in our input, we say we want an input of 10, and the program's like, okay, the answer to that's 54, and you check it and you're like, yeah, it's 54 because the computer knows its stuff. It knows how to do it because it has the instructions in the RAM, which we copied across from the hard drive, HDD, into RAM. It has those instructions, steps through it using the program counter. Program counter, where are you, program counter? Program counter, here it is. It steps through it, and we get our execution, output 54. Everyone's happy. Very cool. Yeah, Kayoshi pointing out the maths there. Very cool. So that's all I wanted to cover, really. If anyone's got any questions or anything wants re-explaining, that's great. If not, then I guess I'll just do a quick summary and then end the stream. How was that, viewers? Is that okay? Not okay? I don't know. Let me know what you think. Oh, I have to wait for stream delay. I should try low latency. One day I'll try low latency and find out. I didn't want to do low latency in case it like completely lags my computer. My computer dies, but I should probably try it because I wouldn't have to wait so long for reply and chat. I don't know. I've definitely got viewers, which is surprising. Well, oh, I just said that I lost a viewer. I don't know. My chat's disappeared. That's okay. All right. I guess I'll just wrap up. How do I wrap up? It's a good question. Where's the thing I want? I wanted my summary. Here it is. We covered everything. CPU executes step by step. We demonstrated that with the program counter. Everyone's happy. So, to conclude and summarize, we've looked at the fundamentals of imperative programming, and what this allows you to do is it allows you to understand both object-oriented programming, which everyone's always raving about, and also procedural programming, which no one really calls procedural programming. We just sort of call programming. But a lot of people are interested to learn programming, so this really sets the ground for that. By looking at sort of a model of a computer that doesn't tell you everything that's in the computer, instead it focuses in on the details that are important. Where's my drawing? Here it is. So the 5 details that I would say are really important to be aware of: the hard drive, HDD, also known as storage, RAM, memory, processor, also known as CPU, and then the input and output nodes, which are essentially what are you putting in, what are you getting out. We looked at how this worked. We looked at the difference between memory and storage, in that memory stores just the things that are currently executing, storage stores everything on your computer, and you tend to have more things in storage than in memory all the time. You have loads of things on storage, but you only execute like 5–10% of everything stored on the hard drive of your computer. We looked at how CPU sometimes gets described as a brain, but that's a terrible idea, and that you should instead think about it as a calculator that runs like 2 to 4 billion calculations per second, and it doesn't do that by user telling it each calculation. You set up a script that tells it which calculations to do. That's essentially what programming is. And we looked at how in a program you execute step by step. In fact, so much so that it forces you to. Like, I literally can't write 2 lines of code on the same thing because you can't execute 2 things at once. It has to be one thing then the next thing. You can only execute one by one in a linear fashion. And I drew a diagram to express this. Where's my diagram? Here's my diagram of it. Literally, the program counter will step through. You can only execute one thing at a time, and it goes through it like that. So there you go. We have now set the grounds for programming. You can go from here and learn all sorts of computer programming. Hopefully this will give you all the prior computer science knowledge about how a computer works that you need to get into computer programming and understand what's going on there. So I hope you guys enjoyed. Tests and loops. Yeah, that's the idea of the next stream about a procedural paradigm, Kayoshi. Yeah, because there's basically different. That's for the next video, really. I'd argue that even with a selection and loops, or tests and loops as you call them, technically speaking, end day it's only going to be one at a time. But yeah, that is another thing to look at. That's what my next video is going to be about tests and loops, or what I would call selection and iteration. But you can call them tests and loops. That's a good way to think about it. Yeah, but at the end of the day, it's only going to be a stream. That's true. If we're getting technical about it, this is just the basics, Kayoshi. But yeah, no, great question. I appreciate question. Yeah, we'll get into that later on. So this should set all the grounds that you need for computer programming, And hopefully you can continue my series or another series on computer programming. This should set all the ground information you need about how a computer works, so you can get onto programming, and when you're programming you can think about what the computer's doing, and that will help you to understand the programming and understand what's going on. If you remember these 4 things about the diagram that I showed, where's diagram? Diagram I showed of the 5 different points that we looked at. If you remember the difference between memory and storage, memory has what's active, storage has everything. And then the CPU is a calculator, is a really important model to think about when you're programming, and that the processor will go step by step through whatever you've written and told it to do. Great. So I hope you guys got something out of this and you enjoyed it. You had a good time. I had a good time. And I'll see you guys very soon for more videos like this, I guess. I sort of spoke about this at the beginning. Where is it? About how we got these 2 videos planned. These ones are harder, much harder to communicate, and I'm a bit of a beginner in communicating things. I'm trying to get better. So I might give these 2, procedural programming and object-oriented programming, a bash at explaining in the future. I might do other topics, I don't know. But yeah, see you then. Bye!